the last example we saw in our first video for linear regression was a random sample of 11 statistics students that compared the third exam score out of 80 as the independent variable to their final exam score out of 200 as the dependent variable. So we wanted the regression line that best fits the data, and if we were to sketch that line by hand, we would draw different lines, but Excel gives us the least squares regression line, and mathematically is the line that best fits the data. And what we discussed is that it best fitting means that these vertical distances of the actual data points from their theoretical data points on the line will be minimized if we are using the line of best fit. And based on that data set, we ended up with a line y hat equal to 4.8274x minus 173.51 with a slope of a equal to 4.8274 and a y-intercept of b equal to negative 173.51. We want to know how Excel graphs this equation and how would we graph the equation by hand if someone asked us to do so. So what Excel does is it actually plots the two endpoints on the line. They correspond to the smallest x value of x equal to 65 and to the largest x value of x equal to 75, and finds the y hats for those x values, and then it just plots this point x comma y hat and this point x comma y hat and connects the 2 points. And this is how this line is designed. And when we want to sketch this line by hand, we will need to find these particular values. For x equal to 65, find the y hat of 140.3, and x equal to 75, find the y hat of 188.5. So how would we find that? We can plug it in the calculator, or we can do a bunch of shortcuts using Excel so that we can calculate these values. So let me just copy my table. I'm going to use Excel as my technology for this chapter because I would like to do more calculator type math, and it very easily can generate the line, which is very easy for me. So here I want to copy somewhere the A and the B. So let's say A equals and B equals. A is the coefficient of x, so 4.8274, and the B is negative 173.51. And notice here that Excel actually rounds. These are not exact values. It has rounded A to 4 decimal digits and B to 2 decimal digits. And I'm going to use those to find y hat for each of the values of x. So I'm going to say y hat equals, and I'm going to say it is equal to A times the x plus the b, ax plus b. And I do want, as I copy for the other values of x and I move downwards in my table, I want those values for a and b to stay the same. So I'm going to put dollar signs in front of the column and the row, just for a and b, not for the x value. I want the x value to come with me as I move. So this is the y hat when x is equal to 65. It is 140.3, and again I round it here, but let me copy down over here, that will be the y hat for, I see that I have errors. Let me see why I have errors. Oh, I do not have errors. I see, I was expecting x to be in ascending order, but it's not. I do have my first point with the minimum value of x be 65 and the y hat to come to 140.3. And I have the maximum value of x to be 75 and the y hat to be 188.5. So this is how Excel will design this line and how I would do it when they ask me how to sketch the line. So the question again is, for these points, how do we calculate the y hat? And the answer is that we plug in the x value into the line and find the y hat. That's the same way that I would find the y hat for x equal to 66, and the same way I would find it for x equal to 69. And here I have had Excel do it for me. So for 66, I would have the 145.1. And for 69, I have two data values. They both have the same y hat because Excel or the line will produce only one y value for an x value. And both of those points you can see in the graph are over here, and they are, one is closer to the line and the other is farther from the line. The one that has the 159, which is the point they gave us in the notes, is the one that is closest because the y hat for x equal to 69 is 159.6. Again, notice that y hat is an estimation of the y obtained by the regression equation, and it is generally not equal to the actual y that I collected from my data set. This vertical error, y minus y hat, is called the residual with the notation of epsilon, which is the lowercase Greek e. And these distances are positive if the y, the real y, is larger than the y hat, so your points are above the line. And they will be negative if the points are below the line. Let's say here that will be a negative residual, and then you will have a y minus y hat being the difference between a smaller value minus a larger value, and it will come out negative. And you can see here that for this particular line, the two endpoints both have a positive residual because they are both sitting above the line. And these will be negative. Let me mark a negative one just for our records. So some notes here. The sum of the residuals equals to 0. And that means that the line of best fit makes sure that whatever is the distance between the points above the line will equal to the distance between the points below the line. Every absolute value of the error is a vertical distance. And again, we said it will be positive if algebraically positive if the point is above the line and negative if it is below the line. We calculate the sum of squared errors, SSE, as the sum of these residuals squared for every single point. If we have n data points, we will calculate this vertical distance. Remember, the distance is the distance of the y's from the theoretical y's, and the line of best fit will minimize those sum of squared errors, and it passes through the point x bar, y bar. X bar, y bar are the average values for the x data values and the y data values. So x bar and y bar are the means of our data points. So using calculus, we can determine the lowest sum of squared errors, and this is what the line of best fit uses to create the line and generate the equation. The line of best fit equation is y hat equals ax plus b, where b is y bar, the mean, average y minus a times the x bar, which is the average of x, and a is the slope. It is the sum of x minus x bar times y minus y bar divided by the sum of the x minus x bar squared. So the numerator of a is the product of the distances of the x's from the mean times the distances of the y from the mean. These are the residuals. And in the denominator is the sum of the differences of the x's from their mean squared. Also, a can be calculated as r times sy over s sub x. S sub y is the standard deviation of the y values. S sub x is the standard deviation of the x values. And r is something called the correlation coefficient, which we will discuss in the next section. Now, I would like to do a little bit of math here and see. They don't pertain to the notes. They are just for encyclopedic knowledge and for practice here with the least square regression line. I want to see if we can actually generate this line ourselves. So if you paid attention here, if I calculate the residuals, which I have to calculate in an order, it will be y minus y hat. I have to do this y, which is the real y, minus this y hat. And then if I copy my formula down, if I add those errors, I will not find them to be equal to 0 when I should have found them to be equal to 0. So the question is, why did I not find them to be equal to 0? I would like this sum of the errors to be equal to 0. It's very close, but it's not exactly that. And the reason it is not exactly 0 is because these a and b values that I wrote here and I copied from the equation that Excel gave me are actually approximations of a and b. Excel had to round to a certain number of significant digits. So I don't have the exact values. If I had the exact values, then my y hats will be more accurate, and also I would also get all the theoretical measures that I was expecting. So I would like to know what is the exact value of a and b if I can, and I have the formulas. So first of all, I need the average of x. So I'm going to calculate that here. I need the x bar. I'm going to calculate it here below the x. So that's the mean. And then I'm going to do the same for the y. So the mean for the x's is 69.18 repeating, and the mean for the y's is 160.45 repeating. And then I'm going to try to generate the formula for a. To find the formula for a here, I need the x minus x bar for every value of x, the y minus y bar for every value of y. I want to multiply those two, and I also want to square the x minus x bars for every value of x. Then I want to add the answers. So let's try to generate the numerator. So first here I will do x minus x bar equals the value of x minus the value of x bar, which is in cell B64. I want this B64 to stay the same, so I'm going to use the $sign. So let's copy this. If I have done a good job, the sum of those distances of the x values from their mean should be 0. this -5 to times 10 to the -14 is a 0, so I'm good enough. That's good enough for me. Let's undo this. I don't like that it extended the width of my cell. So let's try the same for y minus y bar. And that will be equal to the y value minus the mean that is here in the bottom. It's in location C64. I want this location C64 to stay the same, so I'm gonna use the dollar sign, the dollar function, and then let's copy this all the way down. And again, if I have done a good job, then the sum of these will be approximately 0. Let's check. It should be exactly 0, but again, unfortunately, Excel has to do some rounding in its memory. And yes, it comes out to be a 1 times 10 to the -13, so that's close enough. So for the numerator of A, I will multiply x minus x bar times y minus y bar for every value. Let's try this again. So let's say x error times y error. Okay, x minus x bar times y minus y bar. And again, I did this in the wrong cell, so I had to redo it. And let's copy this down. And the numerator is the sum of those, so I do need the sum this time of the product of x errors times y errors for every x value. So it's a 394.091 rounded to 6 significant digits here. And then for the denominator, I need to do x errors squared. So that will equal to the x errors when you square them. And then after I find all those, I have to add them. So equals the sum of those values. So the numerator of A is the sum of 394.091, and the denominator of A is the sum 81.6364 if I have followed this formula. The formula said to add the products x error times y error and to divide by the sum of the x errors squared. So I'm going to try that in Excel and see if it is indeed matches this A. So here I'm going to do the exact value of A. So let's say exact. And it will equal to the numerator divided by the denominator. And you can see here that it is indeed 4.82739. That has been rounded to 4.8274. And here it is also rounded for me to view it. There are even more digits of accuracy in Excel's memory. For the B, I have to make it equal to the mean of y, which is in this cell, minus A, which is above it, times the mean of x. That's again the formula in our notes. And that actually also comes to be -173.513 and some other digits that I don't see. But again, I see how Excel, when it gave me the equation, rounded to some certain accuracy. So I can see how these work. If I find the standard deviation of y and x, and I have found the value of A, I can find this R, the correlation coefficient, which we will be looking at later in this chapter.